Okay, good afternoon. It's Thursday, so we're going to do some more algebra. Picking up where we left off Tuesday, doing some polynomial factoring, and in particular looking at quadratics. We're going to kind of circle back to where we started this series, which is on polynomials in general and simplifying, and we're going to look at rational functions. First thing to know, rational function is another name for functions resulting or involving resulting from or involving polynomial division. Okay, so something is interesting here. If you add, subtract, or multiply polynomials only in the course of creating a new function, the result is a polynomial. If you divide two polynomials, not necessarily. So it could be, it's called a rational function. The result doesn't have to be a polynomial itself. So let's take, for example, there's some polynomial family, 1 over x cubes, go on, 1 over x to whatever power. You could also do like 1 over x squared minus 1. You could also do like x plus 1 over x minus 1. These are all rational functions, different ones. You can tell top and bottom, numerator and denominator here, are both polynomials. One thing to notice, the numerator and the denominator for that matter, they don't have to be, they can be degree 0 polynomials. So for example 1, which we know to think about at times as x to the 0 over x to the 1, say. Okay, so those are some examples of rational functions. Now let's think about simplifying here. So simplify 2a cubed over 7a. What does that equal? Now remember, we're trying to simplify, right? So what we're really trying to do is find a way to write an equivalent expression that is maybe a little bit less going on, a couple fewer operations or simpler operations, easier to do. So we have a bunch of examples. We distributed stuff, we combined things, we now are thinking about maybe executing part of the division. What's really happening in rational functions is that at times, the top and bottom parts of them, they're proportional to each other, right? So you're looking for a part that's going to be consistently either the same through the whole thing or changing at the same time in the same way. That's a way to think about right here. In a being a variable or unknown, a can change. But if a is 5 in the top, it's also 5 in the bottom. You're not allowed to, or we don't use variables with the same letter. We're trying to establish that because we're using a in both places, whatever value a takes, it takes in both places. So although a changes, the relationship between an a on the top and an a on the bottom will be maintained, right? So 5 over 5 or 10 over 10 or 15 over 15, right? So what we want to think about, I think, is first, let's make sure that everyone's on the same page with what exponents really mean. Remember them as a shorthand for repeated multiplication. In a similar way, multiplication is shorthand for repeated addition. So you don't have to write 2 plus 2 plus 2 plus 2. you can write 2 times 4. Here, you don't have to write a times a times a. You can write a to the third power. And what's actually happening here is a form of factoring, I'll argue. What it is something like this. We look for what's in common. There is an a in common, one a in common from top and bottom. Right? The top has 3 a's multiplied together. Bottom only has a single. And what's really happening when we're talking about simplifying rational functions in this way is we're looking for pairs on numerators and denominators that divide to 1. So they're the same, right? And you can separate them out via factoring. And after you've factored, the division can be executed. In other words, yes, that a on top, the a on bottom, contributes to the value of the denominator and the numerator. However, they contribute with equal weight to both, and therefore, when they divide out to 1, it's easier if we can think about just kind of, I don't want to say ignoring them, but their influence will be trivialized because it's the same influence on top and bottom. So what we're really looking at here is a simplification. This is equal to 2a squared over 7. And a cancels from both places, numerator and denominator. Next example. Simplify. 8a to the 5th over 20a to the 7th. First things first, you don't have to do this, but when you're getting back into something that uses exponents in this way, it can be really helpful to recall what exponents mean again, right? So what you can see when you write this out, I think, is that you see there are 5 a's that match top and bottom multiplied together, and they can be factored out. Now, additionally, 8 and 20 have common factor, so they have 4 in common. And 5 a's in common. So you see again, like where factoring is coming in. This is even more peculiar than what we've been doing when it comes to factoring, where we're looking, because if you factor the top or bottom separately, you wouldn't even necessarily do that, right? Like 8a to the 5th is simplified. Yes, it can factor in the sense of like a times 8. A to the 4th or 2a to the 3rd times 4a to the 2nd. There's a lot of different ways to separate a completed multiplication into an uncompleted multiplication, a distribution problem. But we're being very specific here. We're making a specific choice on top and bottom to factor in a particular way. And the way we're choosing is that we're looking for the largest amount that we can find in top and bottom, right? And so what happens then is that those divide to 1. And so we know that this is 2 over 5a squared. I think it's very reasonable to say that this concept is simplification, like looking at what is actually happening to the rational functions to simplify. Now, with rational functions in general, there are some concerns about dividing by 0. So we should kind of start keeping that in mind as we go along here. Like, are there values of a here that are actually a problem because a to the 7th is 0. Yes, there are. Similarly here, are there values of a that are a problem because a can't be 0? All right. Let's simplify that. So sometimes what we get is that the denominator actually divides entirely into the numerator. The numerator is divisible by the denominator. In this case, the numerator 4x minus 24 is exactly 2 times 2x minus 12. So put in any x value you'd like, except for one choice, you will find that the top is exactly twice as large as the bottom. Let x be 0, negative 24 over negative 12, twice as large. Let it be 5, negative 4 over negative 2. Let it be 10, 16 over 8, so on, so on, so on. So it's really quite phenomenal. And this is the case sometimes where we say the word simplify this rational function, and what we actually are able to do is actually execute the division entirely. That's pretty rare. The majority that you'll see, I think, won't be such perfect multiples, the numerator multiple of the denominator, but it can happen. Now, one thing I want to make clear here is this concept of we have a problem. We have an additional concern here. X cannot be 6. If x is 6 here, we divide by 0. If x is 6 here, we divide by 0. And what's interesting is that in order now to say these equal signs are appropriate, they're equivalent expressions, we need to carry with us this x cannot be 6 statement. We can't all of a sudden say 6 is allowed now, right? This is the line y equals 2. It's a horizontal line. And when x is 6, y equals 2 now, because that would mean that it is not an equivalent expression. It has changed, right? In other words, another verification of equivalency, these equal signs that we're establishing along the process of simplification or factoring, is that the graphs need to be completely identical, right? You cannot add or take away any points. You can't change them if you're going to establish an equal sign. And therefore, if the first function fails when x equals 6, then equivalent forms need to also fail when x equals 6. Now this, it's easy to see it because when you try to evaluate it at 6, it breaks. This you try to evaluate at 6, it seems like it should be 2. That's why you have to be thorough and bring along the x cannot be 6 statement. We'll see more of that. Well, similarly, a cannot be 0, a cannot be 0. It actually does happen in this first question as well, where the a cannot be 0 statement needs to come along. Okay. Little erasing. Sorry, accidentally wrote n. simplify this. Well, now I think what we want to establish is that this tricky, nuanced thing about domain restrictions or values of the variables that cannot give you an output or do not give you an output, we should just do it off the bat. Every time, literally every time you come across the rational function, you should be asking the question of, are there values of the variable that make me divide by 0? If there are, then those values of the variable cannot go into the function. So, for example, we find them by finding when the bottom is 0. A useful thing happens is that very frequently when you do this, you have to factor. So m cannot be 0. Cannot be plus or minus 3. It cannot be 3 or negative 3. So we're going to bring that along with us as we complete this simplification. Now, factoring is useful. So the bottom here is going to be m minus 3, m plus 3. The top, m minus, yes, I've made a mistake. Well, you know what? It may be useful to do this and then do the non-mistaken question. The top doesn't factor in whole numbers. It's stuck. And so what we realize in this case is that this is the factored form. There's nothing more to do. Sometimes you roll with a mistake so that you can learn something different, right? Let's do the unmistaken one. M squared minus 6m plus 9 over m squared minus 9. Well, m still cannot be plus or minus 3 because the denominator is the same. This factors m minus 3, m minus 3 over m minus 3 times m minus 3. Sorry, I've never had good handwriting with m's. It's even harder on the touchscreen. Plus 3, sorry. So, those divide to 1. But we still care about our domain restrictions, right? It may seem like in this simplified version, our only issue is m equals negative 3. But plugging in m equals 3 also needs to be a problem in order for these equal signs to be true. And this is really at the heart of a lot of work here, of mathematical work, is to understand at the core the statement of an equal sign, right? That was our first lesson on this channel, of thinking about the equal sign in different ways that it's used. I think the most consistent and most important way, as a math student especially, that an equal sign is used is to say that these two things are the same, written in different ways. Right? These two things are the same, but written in different ways. And so in order for it to be the case that the equal sign is appropriate, that has to be true. So you need to take something like domain into consideration. You can't abandon it as you simplify. All right, let's do a few more. Probably do some more of this next week. I think it's important enough. Rational functions are a rich enough section of material for us to spend a bit of time on beyond one lesson. Maybe we can talk more about domain at some point, because there are a few other domain concerns. Tends to be a very challenging topic, but for me, I've had a lot of success teaching domain compared to some of my peers. I think I want to say that it's kind of because of understanding the equal sign, but we'll see. Let's see here. Let's simplify 10v squared minus 18v over 10v squared plus 16v. Simplify that. Now, this is a very important one to look at, I think. It's very, very important. Because if your first instinct is, oh, look, all I'm doing is I'm matching things that are identical on top and bottom, so I'm going to cross out the 10v squareds, you've made a mistake, right? The problem with that is that 10v squared is altered differently on top and bottom, not via multiplication, via subtraction and addition. Anytime we're trying to divide out to 1 in order to simplify, we need to recognize the importance that we have an expression involving multiplication or distribution in particular. And here we do not have a set of expressions top and bottom that involve distribution. Those are fully distributed polynomials. They're in general form. We need factored forms of polynomials in order to simplify rational functions. So we need a factored form here. One thing to note here, you can check with your calculator. You can check a lot of different ways. No domain issues in this case, except for v equals 0, right? So the factoring here is pretty simple. V equals 0 is a problem. Let me show that, actually. It's probably worth showing. The bottom, we cannot divide by 0. So it's worth that I did it because I was looking at it incorrectly. 2 domain issues, right? V cannot be 0, V cannot be negative 8/5. So now back to the original problem here. We're going to simplify this. First, I want to establish an equal sign after which I've factored. So it looks like 2v can come out of there, and it'll leave 5v minus 9. It's like 2v, we know 2v can come out of here, 5v plus 8. So what we're saying is that this original polynomial division problem, a rational function, is equivalent to this simpler polynomial division problem or rational function. Why is it simpler? Well, we've actually executed some divisions, a portion of the division that is proportional between top and bottom. And so we say that the relationship here between top and bottom is determined entirely by these two lower degree polynomials being divided. So as opposed to a degree 2 divided by a degree 2, we have degree 1 divided by degree 1. It's much simpler. Plugging in v to 5v minus 9 over 5v plus 8, much easier than plugging it into 10v squared minus 18v over 10v squared plus 16v. And as long as we understand simplification, we are establishing as true these equal signs. I think simplifying starts to make sense, and also bringing along domain issues also starts to make sense. We need them to be equivalent expressions in all ways, completely identical when they are expressed, even if they look different, right, when written out or expressed in algebra. When they're expressed graphically, they're identical. So I appreciate you coming by today. Looking forward to next time, and until then,